Hello everyone. In this lecture, I will be talking about the cache memory and its mapping functions. The speed of the main memory is very low in comparison with the speed of the most modern microprocessors. So, it is important to derive a mechanism that reduces the time required to access the necessary information from the memory. The speed of the memory is limited because of the electronic and packaging constraints, and the solution we must devise to sort in a different architectural environment. An efficient solution, a lot of mechanisms has been proposed in the literature. Out of that, an efficient solution is to use a fast cache memory, which essentially makes the main memory appear to the processor to be faster than it really is. So, to discuss the possible methods for specifying where the memory blocks are placed in the cache, we use some specific examples. But before this, we should see the name of the mapping functions. They are, first one is the direct mapping, associative mapping, and set associative mapping. Now, we will consider one example to explain each of these. The assumptions are, a cache, we are assuming a cache consisting of 128 blocks of 16 words each. That means a total of 2048 words are available in the cache memory. And we will take a main memory with 16-bit address. That means the main memory has 64K words, and we can say it as 4K blocks of 16 words each, and the representation of this will be like this. So this is actually the main representation of our main memory. So you can see 4096 blocks are there, and each block consists of 16 words. So that is why it is written 4096 blocks of 16 words are available. Now what we will do? We will group these into like this. That means 0, 1, 2, 3 up to 127, 128, 129 up to, so such 4096 blocks we are placing it in this table. Okay. Now what we will do is, we will divide this memory into 128 blocks. So total we will get 32 such blocks. So in the first segment, we will represent 0, 128, 256. All these blocks will be considered as a single one. And 1, 129, 257 up to 3969. These blocks will be treated as a single one. And the basic principle behind this is the mathematical operation I modulo j. Okay, we are taking each and every block number from this main memory. Then we will perform modulo operation using 128. So the result actually we are representing like this. Okay, 0, 128, 256 all will give you 0. When you perform 128 modulo operation with 128, all these blocks will give you 0, and all this will give you 1, like that. So we are actually performing a grouping operation, and such 32 blocks you will get. Okay, so what we will do is, in the previous slide I told you we have such 4K blocks of 16, in the cache memory we have got 128 blocks of 16 words, 128 block of 16 words. Now what we will do is, we will here, you can see here we have 128 blocks. We have arranged 128 blocks here. Now in cache block 0, what we will write? This is main memory block 0. This is main memory block 128. This is main memory block 256, like that. That is the modulo operation. All the block number who has given 0 after for this modulo operation. All these blocks can be placed in cache memory block 0. Similarly, when you get a remainder 1, that is modulo operation, when you give the when you get the 1, all those blocks we are placing it in cache block 1. Similarly, 127. All these blocks are arranged in this way. Okay. Now, what we will do is, we are actually considering, I told you, 128 blocks of 16 words, and the main memory has, we have 64K words or 4095 blocks as shown in this diagram. This is the main memory, and the main memory is divided into 4095 as I told you earlier. and the cache memory can accommodate only 127 blocks like this. Now we will talk about, or we will think about, the address mechanism. For addressing this 4095 blocks, how many bits we need? We actually need 16 bits for the representation. I mean, if you want to access any of these things, we need actually 16 bits for as the address. So 64K words, word addressable memory. These are the assumptions. We have 64K words and it is main memory is word addressable, and so we need 16-bit address. Okay. Now what I will do is I will divide this 16 bits into different segments. In 16-bit, if you want to divide it into block contains 16-bit address. So here I already told you 64K blocks are there. 64K words are there. Now for that, the block of the main memory actually maps on to block I modulo 128. That also I told you. Thus, whenever one of the main memory block is loaded into the cache, it is loaded into cache block 0 like the previous one. So whenever one of the main memory blocks like 0, 128, 256, etc. is loaded into the cache memory, it is loaded into the cache block 0. Similarly, block 1, 129, 257, all these are loaded into the cache block 1. Here, more than one memory block is mapped onto a given cache memory, given block position. So what will happen? See, in this cache memory, actually here you can accommodate only one block. Similarly, here also you can accommodate only one block. But into block 0 of the cache memory, how many main memory blocks are mapped? We are mapping actually 0. This is main memory block 0. This is main memory block 128. This is main memory block 256, like that. But at a time, only one of these main memory block can be accommodated in cache 0, cache block 0. Similarly, we are mapping main memory block 1, main memory block 129, main memory block 257, etc. to cache block 1. But that is not possible. At a time, this cache memory can accommodate any of these block, any one among these block. Okay, so that is the problem. So how do we place a memory block, main memory block, in cache memory? That we will see. Now what we are doing? For that, the memory address we are dividing it into three parts. Okay, so the low order 4 bits. These low order 4 bits actually select one of the 16 words in a block. I told you 16 words are there. Okay, 16 words are there. In the cache memory, we have 128 blocks of 16 words. So how do we select the 16 words? For that, we are using 4 bits from the low order 4 bits from the address part to select that block, to select that word, I can say. Okay, and when a new block enters into the cache memory, the 7-bit cache block field determines. See, this is the 7-bit cache block. So that actually determines the cache position. So either you can, when you are bringing a block from this main memory into the cache memory, these 4 bits in the address part, these 4 bits in the main memory, the address part, these 7 bits actually represent these 7 bits actually represent to which block, to which cache block the main memory block has to be placed. Okay, and now that means we were talking about these 4 bits. These 4 bits actually determine which word you want to access from this block or from this block. Okay, but these 7 bits actually represent the block number. Okay, where you want to place this block. Okay, that is the block number, and so that is 7 plus 4, 11 bits are there. Now we have one more part left, that is the tag bit, the higher order 5 bits of the memory address. That is actually stored as a 5 tag bit associated with its location in the cache as shown in this diagram. So each block has got a tag. And what is the length of this tag? 5 bits. 5 bit is the length of this tag. And that identify what is the role of this tag? That actually identify which of the 32 blocks that are mapped into this cache position are currently resident in the cache memory. So let us go to the previous slide once more. I told you, when we are dividing the the main memory block, depending on this, what we are doing, actually we are doing a modulo operation to group the main memory block like this. Okay, 0, 128, 256, all these will come under one category, 129. So this is actually we are placing this into here. Okay, so what will happen? What it will do? Actually, this 5 bits, we are talking about that 5 bit. So I already told you, when you divide this 4096 block with 128, how many you will get? As a result, you will get 32. That means we are actually dividing this main memory into 32 segments with each segment 128 blocks. Okay, so that 5 bits will represent from which segment actually that particular blocks belongs to. Okay, that is the role of the 5 bits. I will tell you once more, the higher order 5 bits of the memory address, actually they are the address of the block, are stored as 5 tag bits associated with its location in the cache memory, and that tag bit actually identify which of the 32 blocks, or in other words we can say segment, that are mapped into this cache position are currently resident in the cache. So suppose you want to bring a block from the main memory to this cache memory bit position. Okay, first it will check the tag bits. Okay, so it will check the tag bits, so whether it is available there or not. If it is available there, so we will check the block number. Okay, and we will get the word length. So thus the higher order 5 bits of the address are compared with the tag bits associated with that cache location. Okay, if a match occurs, thus the desired word is in that block of the cache, and if there is no match, the required word with the block must be read from the memory and loaded into the cache. I will tell you once more, the higher order 5 bits of the address are compared with the tag bits, here, tag bits associated with the cache memory. Okay, if a match occurs, thus the desired word is in that block of the cache, and if there is no match, the required word with the block must be read from the memory and loaded into the cache. Thus, this is the concept behind direct mapping. And the advantage of direct mapping is that it is very easy to implement, but the problem is it is not very flexible. Why we are saying it as flexible? Why it is not flexible? A reason I will tell you. You will go to the previous slide. In this case, if you look at this diagram, you can see in cache block 0, what we can do. You can place either main memory block 0 or main memory block 128 or main memory block 256, like that. So any of these blocks can be accommodated in cache block 0. You cannot place main memory block 0 here. You cannot place main memory block 128 here. Consider one case where this cache block is empty. And now we have the like this. This cache block is empty. And this block actually stores main memory block 0. I placed main memory block 0 here. Okay, all other cache memory blocks are free now. Okay, but unfortunately the program that is currently executing requested an information from main memory block 128. So what will happen in this case? we cannot bring this block 128 into this cache memory. Why? Because 128 must be placed in block 0. Block 0, block 128 and block 256 all must come here. You can map all these blocks to only one cache memory block. Okay, so consider we are executing a loop or a function call which is actually changing 128 to 0, 0, 128, 128, 0 like this. So what we want to do, we want to change memory block 0 when the processor requests data or instruction from 128, or when the next time it will be requesting, because we are in the loop or we are calling a function, okay, and again it is requesting the memory location in block 0. So we need to replace 0 and 128 alternatively. So that will reduce the effectiveness of the cache memory. That is why I told you it is not flexible. But all other locations are free also. We cannot place other blocks in this. Because of this, that operation is that the direct mapping technique is like that. Okay, so that's all about direct mapping. Now we will see associative mapping. In this case also, the cache memory we are assuming is having 128 blocks of 16 words, and the main memory consists of 64k words or 4095 blocks of 16 words each. Okay, in this case, if you look at the memory division, you can see to identify, as in the case of previous example, we will use the least order 4 bits. 4 bytes for the 4 bits for the representation of word address, and the remaining 12 bits actually are used to represent the tag bits. That is, in this case, 12 tag bits are required to identify the memory block when it is resident in the cache. The tag bits of an address received from the processor are compared to the tag bits of each block of the cache to see if the desired block is present in the cache memory, and this is called the associative mapping technique. So it actually gives the freedom in choosing the cache location in which to place the memory block. Thus the space in the cache can be used more effectively. How? When a new block comes and we want to brought it into the cache memory, it has to be replaced an existing block only if the cache is full. In this case, we need an algorithm, and we will see that algorithm later. The cost of an associative cache is higher than the cost of direct mapped cache. Why? Because we are actually performing a search operation in this 12 tag bits. So the cost of associative mapping or the cost of search, because of the cost of search, the associative mapping makes it more complicated than direct mapping. And next we will see the set associative mapping. Actually, this is a particular example of set associative mapping. Two-way set associative. That means in this case we are using two sets. Okay, we will see in this one. See, in this case we are dividing the cache memory. We know it contains 128 blocks, but we are dividing this cache memory into sets, each set containing 2 blocks. So totally you will get 64 such blocks. So if you want to represent such 64 blocks, we need how many bits? We need 6 bits. So as usual in the previous example, we will use 4 bits for the representation of word in each block. Okay, and the 6 bits are actually used to represent the set, and the remaining 6 bits, they are actually used as the tag. So when we are placing, or when the computer is generating, when the processor is generating an address, it will take the set field and it will check where that set is located, and then it will look at the tag. So if we are searching for set 64, it will search in this tag. So if the tag bit is there, that block will be, the data is present in that block. That is the case of set associative mapping. So in this case, I already told you, we are considering the number of blocks in a set as 2. That is why it is called two-way set associative mapping. But you can change it. So in that case, k-way set associative. That means the number of blocks per set is a parameter that can be selected to suit the requirement of a particular computer. A cache that has k blocks per set is referred to as a k-way set associative cache. Now we will see the comparison of different mapping schemes. We have seen these three techniques. We have seen direct mapping, we have seen associative mapping, we have seen set associative mapping. And direct mapping, you can see the cost is very low and the flexibility is also low. Because the cost is low because it is very simple. So naturally the cost will be, we don't need any hardware circuitry to implement that logic. So the cost is low. But the flexibility is low because you have only fixed blocks to place. And associative mapped, actually it is cost is high because we are using tag search. That is why the cost is high and the flexibility is also high. But in set associative mapping, the medium, the cost is medium, also the flexibility is medium. You can see if you compare associative mapping and set associative mapping, the searching operation in set associative mapping, you have seen 12 bits are used as the cost, for representing the tag. But in set associative, what we use actually only 6 bits for representing the tag. Okay. Now we will see the replacement algorithm. In a direct mapped cache, the position of each block is predetermined. Hence, no replacement strategy exists. It is clear. And associative and set associative cache, there exists some flexibility. That means we want to place cache blocks, we want to replace cache blocks. When a new block is to be brought into the cache memory and all the positions that it may occupy are full, the cache controller must decide which of the old blocks to override. This is an important issue because the decision can be a strong determining factor in system performance. Thus, efficient replacement algorithms are needed. In general, the objective is to keep blocks in the cache that are likely to be referenced in the near future. So, we will see the cache replacement algorithm. LRU is one such cache replacement algorithm. Because programs usually stay in localized areas for reasonable periods of time, there is a high probability that the block that have been referenced recently will be referenced again. Therefore, when a block is to be overwritten, it is sensible to override the one that has gone the longest time without being referenced. This block is called the least recently used block, and the technique is called least recently used replacement algorithm, or in short, LRU replacement algorithm.